Microsoft just told the world that quantum computing is arriving 4 years earlier than promised, and almost nobody outside the company believes the reason why. In a single announcement, Microsoft collapsed a 2033 target down to 2029, claiming a breakthrough so significant that it rewrote its own roadmap overnight. That alone should stop you in your tracks, because tech giants do not casually slash years off a timeline unless they think they have found something extraordinary. But here is the uncomfortable part nobody is talking about enough. The same physicists who study this exact technology are looking at Microsoft's new chip and saying the company has not actually proven the one thing its entire plan depends on. If that sounds like a contradiction, it is. And that contradiction is exactly why this story matters right now. This all centers on a chip called Majorana 2, unveiled at Microsoft's Build Developer Conference in San Francisco. The chip is the second generation of Microsoft's attempt to build what is known as a topological qubit, a fundamentally different approach to quantum computing than the one used by companies like Google or IBM. Chetan Nayak, the physicist who leads Microsoft's quantum hardware division, said the company is accelerating its roadmap because of what he called rapid progress. His exact words were that Microsoft has cut its timeline in half and now aims to reach a scalable practical quantum computer by 2029. Think about that claim for a second. Microsoft is not saying it made incremental progress. It is saying it found a shortcut so powerful that 4 years just disappeared from the calendar. If you're even mildly skeptical by nature, your alarm bells should already be ringing. Like and subscribe right now if claims like this make your eyebrows go up, because this story only gets stranger from here. To understand why this claim is so explosive, you need to understand what Microsoft is actually betting on. Every quantum computer needs qubits, the basic unit of quantum information, and qubits are notoriously fragile. The slightest vibration, temperature fluctuation, or stray electromagnetic field can destroy the delicate quantum state a qubit depends on, and that fragility is the single biggest obstacle standing between today's experimental machines and tomorrow's practical ones. Most companies are trying to solve this fragility problem by piling on more and more qubits and using software to correct the inevitable errors. Microsoft chose a completely different path. It is trying to build qubits that are naturally resistant to errors at the hardware level using a strange and exotic particle called a Majorana zero mode. These particles are not your everyday electrons or photons. They are theoretical quasi-particles that emerge only under extremely specific conditions, inside ultra-cold superconducting wires, where electrons start behaving collectively in ways that protect quantum information from outside noise. In theory, if you can reliably create and control these Majorana states, you get a qubit that is naturally shielded from the chaos that destroys ordinary qubits. The problem is that nobody, anywhere, has definitively proven these Majorana zero modes actually exist in a working device. Microsoft has spent close to 2 decades and enormous sums of money chasing this exact goal, and the company's track record on this specific claim is genuinely rocky. Back in 2018, Microsoft had to formally withdraw a paper published in the prestigious journal Nature after independent researchers found the evidence for Majorana particles did not hold up under scrutiny. Then, in 2021, and again in 2025, the company faced further retractions and corrections tied to the same underlying claim. This is not a minor technical footnote. This is a company asking the world for the 3rd time to trust that it has finally cracked a problem it previously got wrong, publicly, in peer-reviewed science. To put the difficulty of this challenge in perspective, you have to understand why almost every other major player in quantum computing avoided this approach entirely. Google, IBM, and most of the well-funded quantum startups chose to work with superconducting qubits, or trapped ion qubits, technologies that are already proven to exist and already demonstrably work, even though they remain fragile and error-prone. Microsoft looked at that entire landscape years ago and made a contrarian bet, deciding to chase a particle that existed only on paper, in theoretical physics models from decades earlier, rather than build on technology everyone else already trusted. That is either visionary long-term thinking or a stubborn sunk cost trap, depending entirely on whether Majorana zero modes turn out to be real and controllable. There is no safe middle ground in this bet. Either the topological approach eventually outperforms every competitor because its qubits are naturally more stable, or Microsoft spends another decade and billions more dollars chasing a particle that may never cooperate the way its physicists hope. That history is exactly why the physics community reacted to Majorana 2 with so much caution instead of celebration. If a claim has already been walked back twice before, hit that like button because skepticism is earned, not handed out for free. So what actually changed with Majorana 2 that made Microsoft confident enough to cut its timeline in half? According to the company, the new chip swaps out aluminum for lead as its superconducting material and updates the semiconductor layer using a combination of indium arsenide and indium arsenide antimonied. Microsoft says This new materials stack created a more stable topological phase, and the headline number the company is promoting is a 1,000-fold improvement in qubit reliability compared to the first-generation Majorana chip. Specifically, Microsoft claims the qubits on Majorana 2 maintain their quantum state, called parity, for an average of about 20 seconds, with some instances stretching out to a full minute. Compare that to Majorana 1, where the equivalent lifetime was measured in milliseconds, and on paper this does look like a genuinely massive leap. Microsoft also revealed that artificial intelligence played a direct role in this progress through a platform called Microsoft Discovery, which uses AI agents to automate the painstaking process of tuning hundreds of device parameters and measuring quantum states, a job that used to take human researchers weeks to complete by hand. The company says these AI agents cut measurement cycle times by orders of magnitude, building three-dimensional maps of device conditions that a single scientist working alone could never have produced at the same speed. According to researchers involved in the project, earlier attempts to automate this exact measurement process using older forms of machine learning had failed outright years. Ago, because the pattern recognition required to detect subtle shifts in electron behavior across billions of particles on a semiconductor wire, proved too complex for those earlier tools to handle reliably. On the surface, that combination of better materials and AI-accelerated research sounds like a legitimate reason for optimism. But here is where the story takes its sharpest turn and where you need to lean in. Outside physicists who reviewed Microsoft's published data are not disputing that the materials improved. What they are disputing is something far more fundamental, and it strikes directly at whether Microsoft has built a qubit at all. To prove a topological qubit actually works, researchers need two distinct types of measurements, known in the field as Z measurements and X measurements. Z measurements check the parity state of a single wire in the device. X measurements check the joint parity across both wires of the structure, and that second measurement is the one that actually proves the qubit can store and manipulate quantum information the way a real qubit must. According to independent analysis of Microsoft's new preprint, the Majorana 2 paper presents only Z measurements. The X measurements, the ones that would prove this is genuinely a working qubit, are simply absent from the data Microsoft released alongside its bold 2029 announcement. That is not a small detail buried in a footnote. That is the entire ballgame. Here is why that missing measurement matters so much more than it might sound on the surface. A Z measurement can detect whether a parity state exists and how long it survives, which is impressive and worth publishing on its own. But a qubit is not just a particle that holds a state quietly. A qubit has to let you read information out of it and manipulate that information in a controlled way. And that is precisely what the X measurement is designed to prove. Without it, what Microsoft has technically demonstrated is a very stable, very long-lived physical state inside a wire, not a device that computes anything yet. Interestingly, Microsoft did publish X measurement data for the earlier Majorana 1 chip in a separate preprint released back in July of 2025, several months after the original Nature paper had already drawn heavy criticism. That data also failed to convince skeptics like Froloff and Legg, who argued the X measurements themselves carried interpretive problems. With Majorana 2, the new and supposedly far more advanced chip, that same critical category of evidence is simply not present in the paper at all, and the document explicitly describes investigating these effects as future work still to be done. If a single missing measurement could be the difference between a real breakthrough and a marketing headline, smash that like button, because this is the part of the story most coverage glossed right over. Sergei Froloff, a quantum researcher at the University of Pittsburgh who has tracked Microsoft's Majorana claims for years, did not hold back when describing the scientific community's reaction. He said that when Microsoft is mentioned in physics circles these days, researchers tend to just chuckle or raise their eyebrows, and he pointed out that Microsoft's previous preprint of this kind has remained unpublished in any major journal since last summer, which he interprets as a strong signal that top journals have likely rejected it. Another physicist named William Legg, who has publicly doubted Microsoft's earlier claims, goes even further, arguing that the company may not have a functioning topological qubit at all, given the absence of those critical X measurements. Meanwhile, a 2025 Nature paper on this same research came attached with an unusual editor's note, explicitly stating that the results in that manuscript did not represent evidence for the presence of Majorana 0 modes in the devices being studied. And yet, despite that editor's note, Microsoft's own press release at the time claimed the team had obtained exactly that evidence, and most of the nuance and caveats got completely lost in the media coverage that followed. Do you see the pattern forming here? A peer-reviewed journal attaches a formal disclaimer saying the evidence is not there, and the company's marketing department announces a breakthrough anyway. Not every scientist is dismissing Microsoft's progress entirely, and fairness demands we say that clearly. Kartiek Agarwal, a physicist at Argonne National Laboratory, reviewed the new measurement method Microsoft used to probe the non-local properties of these particles and called it fantastic progress, saying it does support the case that the company may genuinely be observing real Majorana behavior. Even some of Microsoft's harshest critics acknowledge that the materials engineering inside Majorana 2 looks like a real and impressive achievement on its own terms, regardless of whether the topological interpretation eventually holds up. Replacing aluminum with lead and achieving that 1,000-fold improvement in parity lifetime is not nothing, even to skeptics. The disagreement is not about whether Microsoft built better hardware. The disagreement is about whether better hardware automatically means a working qubit, and on that specific question, the company and its critics remain miles apart. Microsoft itself is not backing down from any of this scrutiny, and that confidence is worth examining closely. If you think confidence alone should not be enough to justify a 4-year timeline jump, you already understand exactly why this debate refuses to die, so go ahead and hit subscribe. Chetan Nayak addressed the criticism directly in public statements, essentially arguing that physics doubts are a normal part of pioneering work. Nobody else has successfully done before. A colleague at Microsoft named Xander pushed back even harder against critics, stating plainly that the team would not be spending this kind of money on engineering if they genuinely believed the underlying physics was still uncertain. Microsoft has also pointed to its involvement in a multi-year quantum program run by DARPA, the United States Defense Research Agency, which was specifically designed to independently test whether utility-scale quantum designs from companies like Microsoft actually function as claimed. The company says it handed DARPA everything, including sensitive commercial material that competitors never get to see, as a way of proving it has nothing to hide. Yet even that DARPA relationship has not satisfied outside reviewers, because the new Majorana 2 paper supporting the 2029 timeline has not been peer-reviewed, and scientists who examined it for international outlets like the BBC have publicly said they want significantly more data before accepting Microsoft's framing of the result. It is worth pausing here to understand exactly how much money and how many years are riding on this single scientific question being answered correctly. Microsoft does not disclose a precise dollar figure for its quantum research program, but industry analysts who track corporate research spending estimate the company has poured well over $1 billion into this specific topological approach since the project began, spanning specialized cleanroom facilities, custom fabrication equipment, and a dedicated team of physicists based primarily out of Santa Barbara, California. That level of sustained investment, continuing even after 2 embarrassing public retractions, tells you something important about how confident Microsoft's leadership remains internally, regardless of what outside critics are saying in scientific journals and conference halls. Confidence alone does not make a particle real. But it does explain why the company keeps doubling down instead of quietly walking away from a bet that has already cost it credibility once before. This is the core tension driving the entire story. A company with virtually unlimited research funding is racing to be first in a field where being first carries enormous commercial and political weight, while the scientific process that is supposed to validate extraordinary claims is structurally slower than a press release. Microsoft Build happens once a year. Peer review can take many months, sometimes longer, especially for a claim this contested. That mismatch in speed is exactly how a 4-year timeline acceleration can dominate headlines worldwide within hours, while the actual scientific verification needed to justify that acceleration is still sitting unfinished, months or years away. There is also a wider race underneath this specific controversy that makes the timing especially loaded right now. The United States cannot afford to lose. That framing matters, because it transforms a purely scientific disagreement about Z measurements and X measurements into something with national and geopolitical stakes attached. When a technology gets tied to great power competition, the pressure to announce progress quickly tends to increase, even when the underlying science would normally demand more caution and more time before any public claims get made. This pattern is not unique to quantum computing either, and that wider context is worth a moment of your attention. Time and again in modern technology history, the gap between a press release and a peer-reviewed confirmation has been where the real story actually lives. Battery breakthroughs, room temperature superconductors, and certain medical research announcements have all followed a strikingly similar arc in recent years. A bold claim generates global headlines within hours. Independent experts spend months or years quietly checking the actual data behind the curtain, and only afterward does the public find out whether the original claim survives that scrutiny intact or quietly falls apart. Quantum computing, because it combines genuinely difficult physics with enormous financial incentives, and now geopolitical pressure as well, may be one of the most extreme versions of that pattern playing out anywhere in technology today. So where does this actually leave us? Sitting here in the middle of 2026, watching this unfold in real time. Microsoft has released Majorana 2 to the public, and the broader platform behind its development, called Microsoft Discovery, is now generally available for outside researchers and developers to use through GitHub. That alone is a significant move because it means independent groups outside Microsoft will eventually get the tools to test similar approaches themselves, which could either validate or undermine Microsoft's claims faster than waiting on Microsoft's internal papers alone. The honest, unhyped summary of where things stand is this: Microsoft has genuinely improved its hardware. That part is not seriously disputed by anyone. The materials are better, the reliability numbers are dramatically higher than the previous generation, and the AI-driven research process behind it represents a real and interesting use of agentic systems in experimental physics. What remains unresolved, and what nobody can responsibly skip past, is whether any of that hardware improvement actually proves the existence of a working topological qubit, the single foundational claim that Microsoft's entire 2029 timeline depends on. Until independent labs replicate these results, until Microsoft releases the missing X measurements that critics keep asking for, and until a peer-reviewed journal puts its name behind this specific paper, the responsible position is to treat this as an exciting but unproven bet rather than a settled scientific fact. That distinction matters enormously because the difference between those two things is the difference between quantum computers transforming medicine, cryptography, and material science by 2029, or this becoming yet another chapter in a string of premature announcements stretching back to 2018. What we do know for certain is that the stakes attached to getting this right or wrong have never been higher. Quantum computers, powerful enough to fulfill Microsoft's promise, could eventually break much of the encryption protecting the modern internet, simulate molecules well enough to accelerate drug discovery in ways classical computers simply cannot match, and solve optimization problems across logistics, finance, and energy that currently take today's most powerful supercomputers an impractical amount of time to even approximate. That is precisely why a 4-year acceleration claim, even a contested one, sends shockwaves through scientists, investors, and governments simultaneously the moment it gets announced. Consider just how disruptive a working version of this technology would actually be across industries that have nothing to do with physics research at all. Pharmaceutical companies have spent decades simulating how molecules interact using classical computers, a process that often takes years and consumes enormous computing budgets just to test a handful of promising drug candidates. A sufficiently powerful quantum computer could theoretically model those same molecular interactions in a fraction of the time, potentially compressing years of laboratory work into weeks. Financial institutions face a similar story with portfolio optimization and risk modeling, where the sheer number of variables involved currently forces banks to rely on approximations rather than exact calculations. National governments, meanwhile, are watching this entire field through a security lens because a quantum computer powerful enough to break current encryption standards would force a global overhaul of how sensitive data, financial transactions, and even military communications are protected. None of these outcomes depend on whether Microsoft specifically wins this race. They depend on whether anyone, anywhere, actually builds a fault-tolerant quantum computer at meaningful scale. And that is exactly why every claimed acceleration toward that goal draws this much scrutiny and this much attention all at once. The real catch, the one underneath every other catch in this story, is this: Microsoft is not just racing toward a working quantum computer anymore. It is now racing to defend the credibility of its own roadmap in full public view against a scientific community that has watched this exact company walk back similar claims not once but twice before, and that is now demanding proof instead of promises before it grants the benefit of the doubt a third time. If this story changed how you think about every confident tech announcement you scroll past without a second thought, that is exactly the point. And that is exactly why you should like this video. Subscribe for more deep dives like this one, and stick around because the next breakthrough claim, real or not, is already on its way. And you will want someone keeping score when it lands.